So you see, this is like the first step when you ask a math question. You start to like realize that it could be messier than you like.
Your initial question is just, okay, how many times do they intersect? Well, you have to put some sort of a boundary on that. You have to kind of narrow it down.
Triangular numbers map out like the way things can interact with each other. The key, I think, is realizing why the pattern's there. I think that is like what like mathematicians like to see. They're like, oh, there's this pattern.
Okay, right.
That's exactly what the sort of question you should ask in a math class. You should say like, wait, did we prove this all the way? This started off as like a really simple problem that you can probably solve in one sitting, but the more I thought about it, the more interesting it was.
Hello and welcome to the Making Mathematicians podcast. I'm Zach and I'm here with my brother Alec and my sister Cass. We're the creators of Making Mathematicians. It's an online course that shows homeschool parents how to learn and teach real math. In this podcast, we're going to be answering your questions about how to learn and teach real math. If you'd like to learn more, check out the complete Making Mathematicians course at makingmathematicians.org. Welcome back to the podcast. We've changed our format a little bit. Now we're doing it over Zoom, but it should be the same. Everything should run smoothly. We're just kind of doing different technical things.
We shouldn't talk over each other as much. Oh, wait.
Oh.
There, just wait.
No, that'll happen no matter what. That'll always happen. Today, so we're a bit different technically, but we're also doing a bit of a new format where we're going to have a little math club. Today, Alec's going to walk us through some math he's been working on. So, Alec, take it away.
Right. My idea, we've talked a little bit about this, but my idea was in the course, we talk about doing a math club. I think it's really important to do math with other people, not just by yourself. That's part of the whole mathematical paradigm. That's how mathematicians work, generally speaking, not Uncle Petros, as we learned a few weeks ago. But that was a problem. That was, I think, one of his problems, is that he was sort of approaching it as... So anyway, in the course, we talk a little bit about the importance to do math with other people. And one of our suggestions is kind of starting a math club. If you have, friends, maybe other homeschool families who are trying to study real math. And so one of the things we wanted to do in the podcast was to model this, like what a math club can look like. And it's really open-ended. I don't want you to think that you have to do like X, Y, and Z. If you have a math club, you could just read books like we sometimes do here on the podcast as well. But I wanted to kind of explore different things that you could do in a math club. And kind of the most obvious thing you could do is present what you're learning in math or problems that you're working on, or that sort of thing. So that's what I kind of wanted to showcase today. And so I'm just going to show a really simple problem. This is actually a few weeks ago. I mentioned a problem, just something that I think the night before we recorded, this was probably like a month or two ago. The night before I recorded, I was sort of, lying in bed thinking of lines on a plane. And I remember I mentioned this, and then I tried to explain it off the top of my head, and I did a horrible job, and it was completely confusing. So I thought I could go back and actually explain that in a way that's coherent. The point of this episode, really, the point of all these Math Club episodes, I think we've talked about doing maybe one a month or something like that. Is the point of this all is to show you what it looks like to do a math club. So I'm really not going to try to do anything technical. I'm not like a great mathematician myself, but I'm even going to keep it kind of at a simple level for me, because I want to get to the end of this and I want you to feel like, oh, I could do that. Like that's the feeling I want at the end. I can do that, and I want to do that would be a nice added bonus. But at least I could do that. Is what I'm going for. So you guys can sort of keep me honest. If I make any like logical jumps or assumptions or anything, you can jump in and tell me to stop.
I've spent the day wrangling kids, so the goal is to, if I can follow it, hopefully other parents with, after a day of, or in the middle of a day of working with their kids, hopefully the goal is for everyone to be able to follow this and to work along with it and to understand and participate.
Yeah, Cass.
And I'll just
because we're at a low bar for understanding, so it's perfect.
And not just follow. I'm going to try to keep this simple enough that you can see that this is a sort of problem you could sort of work out yourself. So we'll see how that goes. Also, like all math problems, I could probably just like keep going down this rabbit hole for a while. So you'll just have to stop me when you're like, this is boring now. It won't get boring, but this is too much. So the one caveat for all of these Math Club episodes is that there's going to be like a visual component. I'm just going to be doing some drawing and writing and stuff, because otherwise this would be impossible to explain. And that's pretty standard. Even if you read a math paper, there's often little drawings and stuff, little equations that you kind of need to look at. So most of our episodes you can listen to just as easily as you can watch. This one you can try to listen to it, but odds are I'm guessing you're going to have some trouble following along. So this is going to be one that maybe you want to watch on YouTube, or I think YouTube is the only place we're uploading video. So that's an important caveat.
Unless you have just a very rigorous mental
a really
system.
Good visual imagination, much better than mine. All right, so let's jump into this. I'm gonna go down to my iPad here. You guys can see what I'm doing. I'm just gonna trust that you guys can see what I'm doing. All right, so what I was talking about, the problem, the question or whatever, is I was imagining if you had a plane, just like a flat surface, and you started drawing lines on it. Say, I'm just gonna use a pencil. That feels, there we go. You start drawing lines on the plane. I'm gonna hopefully do this in a way that doesn't come back to bite me. And in theory, like, a plane is a flat surface and lines are gonna go on forever. And so my question was, as I was lying in bed, not able to sleep, as you guys know, I don't get very much sleep. This is the sort of thing I think about. The question I had was how many, if you have like a certain number of lines, so in this case, I just drew 4 lines, right? Yeah, 4 lines. And so the question is, how many intersections would there be, right? How many like points between the lines? So like there's 1 point, whoa, that's way too big. There's 1 point, 2, 3, 4, I just missed that 5, and 6 in this case, right?
I thought you were gonna
so
miss
that
the
was my
6th
question.
one.
I almost did. So that's why you don't just count things in math. You want to find proofs for things, because you can make little, even mathematicians make arithmetic and counting mistakes or whatever. So anyway, this was my question as I was thinking about this, and it's, again, I'd like this question because it's really basic. I think you guys understand this, right? You get what I'm going for.
Yeah.
It, like, intuitively, it seems like if you have a certain number of lines, there should be like a specific number of intersections. I realized as I was sitting and thinking about this, I don't know how much I have space here, that this isn't the case. Like, for example, if you have, I switched to a pen. If you have 2 parallel lines, right, they're never going to intersect. And so there's parallel lines, and then I realize there's also a possibility of, like, if you have, 3 lines that all intersect at the same point, then that's going to be 1 fewer intersections. So as I thought about this, the way I decided to formulate it was, what's the maximum number of intersections you could have, right? Because that'll eliminate parallel lines or like overlapping intersections. So you see, this is like the first step when you ask a math question. You start to like realize that it could be messier than you like, and that's okay. You can work with the messiness. Like, for instance, I think there is actually some interesting patterns with parallel lines when I was thinking about it, but I won't get into that today.
So you could you start with, you might start with how your initial question is just, okay, how many times do they intersect? Well, you have to put some sort of a boundary on that. You have to kind of narrow it down. And so you could start with, well, how, could we have them intersect the fewest number of times? And then you solve that pretty quickly by saying, well, if we made them all parallel, they would never intersect. So then you jumped to the opposite spectrum, which is, okay, how many, like, what's the maximum number of times they would intersect? Okay. Yeah,
you could really, what I did in this case was I was imagining a case where none of them were parallel, and then when I realized that there was that exception, you can just like legislate it out. You can just be like, that's not what I mean. Just in this case, I think like the idea of like what's the maximum number that you can get kind of simplified it. Go ahead.
Oh, I was gonna say in this scenario, and that's an example. Like, obviously, like you said, you can just legislate it out. Like, you have to put parameters on it because you're just playing around with something. And what's interesting isn't you finding like there is no correct answer. You're just playing around with lines. What's interesting is like how these imaginary objects have a level of consistency when you can do random things with them. So I think that to me that just showcases like it's not about you're not looking for a very specific destination. You had an idea, you had a mental image, you start drawing it down and you start playing with it, and to see ways that it seems to interact or it seems to act like objectively even though it's an imaginary object.
Yeah, exactly. And of course, you can go the other direction, right? Like, you can say, like, oh, what if we include parallel lines or overlapping intersections? Or, what if we allow for curved surfaces instead of the plane? Or what if we allow the lines to curve or whatever? You know what I mean? You can always go the other direction. That adds a lot of complexity really fast. And the more complex the question, like, the harder it's going to be to solve it. So
But
that's just something
potentially,
to be aware of.
I guess if let's say you start working on it and you make it really simple and then you solve it too easily, but then you're like, what else can I do with this? Then you could slowly add, we've talked in the past about like, if you have a question that's too complicated, like bring it down a few notches, but you could also do the opposite. And if you're like, that was too easy, like what else can I do with this idea? You can complexify it.
Yeah.
Work?
Complexify. It works. So in this case, it really wasn't too tricky to figure out what was going on. Like I said, I'm choosing this because it's a simple example, but what I just started doing is I just started like using examples. That's often like the best way to start. So one line here, I'm gonna write here like lines, and create a little graph here. Lines and intersections. Just read that. So we have one line there and 0 intersections, right?
Mm-hmm.
And then I added a second line, and then we have 1 intersection. 2, 1.
And there only can be one intersection with 2 straight lines on a flat plane.
Exactly. Okay. Well, there could be 0, right? If they were
rules.
parallel.
That's true. Mm-hmm.
Yeah,
but
that's the maximum.
We're looking for the maximum.
Yeah, and the way to get the maximum is to make sure they're never parallel and they never that they're always intersecting. And so then I'm gonna add like a third line, and there we're gonna get 2 and 3. So
and we could
3
just
lines.
have that line intersect with 1. Actually,
yeah, if it were parallel, but if it were parallel with the first line, for example, it would only.
Oh, it would have to be parallel with one of the lines.
But assuming these lines are continuous, the lines we have are finite, and therefore you could just move it so it was.
Oh yeah, that's okay. That's another rule you
parameter.
Could legislate for. Yes. I don't think legislate is the right word. Parameter is a better word.
Wait, so are we assuming these lines are infinite?
Yes, I am for now.
Okay.
But if our goal is to find the maximum number of intersections, then it doesn't matter. The maximum number of intersections are going to be infinite. So
we're not
1,
deliberately
2, 3.
trying to move this in a place where it won't intersect.
So like we said before, 4 lines, we have 6 intersections. And by this point, I was starting to like think of this like what's happening every time we draw a new line, right? If we draw a 5th line, we already have 6 intersections, so it's essentially going to be like additive, right? And a new line is going to go through all the previous lines one time, right? So we were at 6, so this is going to be 7, 8, 9, and 10. So 5 lines makes 10 intersections. And the way to think about this, the way I started thinking about this is like, oh, you're just essentially adding the total number of previous lines to the previous sum each time, right?
Okay, I see that.
It's going. So every time you draw a new line, let's see if I can draw a 6th line. It starts to get confusing. When I first did this, I was trying to do it in my head, and I had to get up and actually draw this because I was losing count pretty quickly. Let's draw one right here.
No, but that's not going through that line.
You're right. Take it back. Retreat.
It's not quite it's not parallel, but they would eventually intersect, but they're not.
They would eventually intersect.
Mm-hmm.
See, this is my problem. I've already run out of room. Let's do that one. Ready?
Does that hit them all?
Yes. Dang it! I did that. The thing that I legislated against. I broke my own.
What was
my own
that?
code.
Was there
I
an
crossed through a
intersection?
previous intersection.
Oh.
Okay, I think that one went through them all. So where were we? We were
not
at
quite.
10,
That's
it's
pretty
close.
tight there. But...
It's not though. It's not though.
Yeah.
It's close.
10, 11, 12. Wait.
Wait,
Yeah,
what
11,
is that?
12. That's this one here.
Okay.
Then 13, 14. Yeah, I definitely made a mistake.
No, there's where you put 12. There's
Up by
2.
12, there's 2.
Oh, there's 2. You're right.
Yeah.
They're
See?
just it's almost.
It's
what
very
you
close,
said you
but it's
wouldn't do.
technically it's a separate.
It went through that one. So I got to 15. This is 15 here.
Yes.
So
Which matches
line
the
6
pattern.
makes 15. Exactly. So it's essentially 10 plus 5, right?
Right.
So
the
each
next
one of these is
should
gonna be-
21.
Yes, which would be 15.
Oh, I
plus
just
6.
got the pattern. I wasn't following.
Yeah, no. So we have 15.
Okay,
If I
so
added a
Just need a
7th,
couple more iterations. To
if I added a 7th line, it would go through 6 previous lines, right?
Yeah.
So it would be 15 because that's where we're at
15.
now.
Plus
Plus
the 6 previous
6
lines.
because
21.
the 6 previous lines. So
Oh.
the pattern is essentially
It's easier when the numbers are smaller. Like you look at 3 and 3, that's going to be 6 for the next one. 4 and 6, that's going to be 10 for the next one. 5 and 10, that's
Yeah.
going to be 15 for the next one. That's
Yeah.
pretty cool.
Now I am gonna make a bit of a jump that
and the way that you did that was just drawing and recording what.
Well, I was gonna say it was
Like, the chart,
drawing
I
and then
think, is
having
really
a clear. Oh, sorry,
the
like drawing
graph.
it, but then having a clear space where you were kind of showing what was happening.
yeah, and just thinking about that's the key. Like because you could like do this and see that there's a pattern. And that would be one solution because you're like, oh, there's a pattern here. Let's see how long it goes on. And you could just keep going. Like if you're just looking at like these numbers here, you may or may not be able to pick up on that pattern. But the key, I think, is realizing why the pattern's there. I think that is like what like mathematicians like to see. They're like, oh, there's this pattern.
Okay, right.
And so to get back to my original question, which is sort of like
But
where.
can I interject real quick though? Like,
Yeah.
I do think that's interesting though. Like you're saying, so finding like why is that pattern there, and that's kind of. But it's almost like finding a pattern in the first place kind of motivates you to want to understand because it is weird, and this is everything we talk about every time we talk about math. But like, it's weird that we just went from like you're just drawing lines randomly to like, oh, there's a very concrete pattern here, you know?
Yeah.
But so in a sense, I think like the almost the uncanniness of math is like what motivates you to want to like understand it.
No, I watched like a talk. It might have been a TED talk. I don't know. It's just a lecture by Grant Sanderson, who does 3 Blue 1 Brown, which is one of the big YouTube math channels. Where he was talking about different videos he's put out, and he showed one, and it's a weird scenario where you simulate like masses bumping against each other, and they like produce the digits of pi by the way that they like crash into each other. And he sort of explained, he's like, the thing about this problem is that if you're a human being, you have to know why masses bumping into each other produce the digits of pi. It makes like it seems inexplicable. And the proof is kind of complicated, but it's a great video. But I just think that's always funny. Like when you see a pattern and there isn't an obvious reason for it, like you've got to know. And again, this is much simpler. Again, this is the sort of thing I hope that anybody could figure out if they just kind of played with it long enough. But yeah,
And
you can see
again,
the pattern
the
and you can see
why
the
there-
reason.
You said this a few times, but the why there is because it is intersecting with all the previous lines. So we're just adding the number of previous lines to the current number of intersections because it's got to go through every line that we've already drawn once.
Yeah. And so it's just going to be the previous total plus the previous number of lines. And I think that makes sense. Now, I was going to say...
Zach and I are mind blown, and you're like, I've got more.
Well, no, I mean, it's... Because the original question is, like, given a certain number of lines, like, is there a way to determine the number of intersections? And, I mean, like, you could count, but, I mean, like, given, like, 10,000 lines or something, like, how many intersections would there be?
Okay.
And there's a... At this point, I do have to, like, make a little jump, because this series of numbers is like, pretty well known. If we lived in a world where, like, kids were all taught real math at school, every adult in the world would, like, immediately recognize this series of numbers. These are the triangular numbers, which you may know from our logo, the Making Mathematicians logo. We use that. The Pythagoreans use this as like a symbol of their weird obsession with numbers, right? The I forget what they called it. Some word in Greek. I'm not going to try it because I'll mess it up. But so the triangular numbers are essentially like numbers that you form by forming a triangle. So for instance, if you're looking at the screen, I just made like a triangle of numbers, and like the first one is 1 plus 2 plus 3 plus 4. So this would be the fourth triangular number, and that's equal to 10. So actually my series of these lines is offset by 1. Like there you see 4 lines make 6, but the next one is 10. So it's sort of a little bit cheating, because like I already know what the formula for for the triangular numbers are. The best way to think about it is triangular numbers are going to be about half of a square number, right? In the same way that, like, if you have a triangle and you have a square of the same base and height, the triangle is going to be half of the square. So in the same way, the triangular number is about half the square. It doesn't line up perfectly, so it's actually like, instead of, like the fourth triangular number isn't 4 times 4 divided by 2, that'd be 8. It's 4 times 5 divided by 2. So the way you write this is like n times n plus 1 divided by 2. So for instance, putting 4 in there, it's 4 times 5 divided by 2 equals 10. And that's how you can compute any triangular number. Like I said, I know that off the top of my head, but if you didn't know this, say you just got this series here, and you didn't know
which
anything
I didn't know
about it
off the top of my head. It rings a bell once you're describing it. I'm like, oh yeah, no, I learned that. But
one thing you could do, and something I've done with like other problems, is, ready for this? You could go to the online encyclopedia of integer sequences, which I just love because it exists.
That's really cool, actually.
It like looks like a website from when I was a kid. Back then. And you can just like plug in your integer sequence. So we had 0, what was it, 1, I think 0, 1, 3, 6, 10. I'm trying to remember. It was 15 and then 21, right? Mm-hmm. So you can do that and search it. Just plug in what you get. And sure enough,
28,
we get 21, 28, 36, 45. It goes on forever.
The numbers are very small on my phone now. I'm having to like leave the frame to see.
Sorry. I can zoom in here.
Oh, that works. Thanks.
See? And it has that formula right up here.
Oh yeah.
It'll tell you how to generate them. There's a famous story. This is totally off topic. There's a famous story of Gauss, Carl Friedrich Gauss, when he was a kid. Supposedly, like his teacher, when he was in school with like a rowdy class, his teacher told him, it just told them to like add all the numbers from 1 to 100, because the story is the teacher didn't want to like actually teach them anything. I'm like 90% sure this is a made up story, but supposedly Gauss solved this problem, because that would be the 100th triangular number, and supposedly Gauss solved this problem in a few seconds because he had already devised this formula for coming up with the triangular numbers.
So you explained this formula, but you did it a little quickly. And I confess I didn't follow it. Can you go back and show us the triangular number formula and how, because why is it offset by 1? What's going on there?
Well, the way to think about it, right, is, so here we have the fourth triangular number, right? You see, I made a little triangle of it, but you could, I wonder if I can use different like colors. So here, I'm going to kind of redraw it slightly differently, but recognizably the same. Right, so that's 10. That's what we're going for. And then you can, the way I've seen this done, just pick a different color, is you essentially fill it out to create like a rectangle. So there's the same number of green and black dots now. And that way it's 4 times 5, right? 4 down this side and 4 plus 1 down this side. And then it's just half of that. So that's I think that's the easiest way to think about it. Does that make sense?
Why did we do that though?
Because then it's multiplication.
Hang on, so what's the question we're trying to do?
Good question.
With the triangle?
We're trying to find the number of black ones.
Okay.
Right? Say we're trying to find the triangular number, the fourth triangular number. So we make a triangle that's 4 stacks tall, and then we double it.
So we're trying to find the total number of dots when we dot.
Yeah.
We're trying to create essentially a shortcut, a formula for knowing at a glance, basically, how many dots are in this triangle we've created out of dots.
Yeah. Because now it's 4, so we can just count it.
Okay, there's 4. So what's the equation basically that will tell us what's here?
Yeah. That's that n times n plus 1. So in this case, sorry, I did go through that kind of fast. I was sort of not planning on explaining it, but that's fine. This is how I visualize it. There are other ways you can visualize it kind of algebraically, but I like the visual representation. So we essentially doubled the triangle and then flipped it on its head so that it fits and it becomes a rectangle, because then we can use multiplication. Because rectangles you can figure out with multiplication, right? So this rectangle is 4 tall. Use my little laser pointer. It's 4 tall and it's 5 wide. So it's going to be 4 times 5. And then it's half of that, because that's the whole point of this. And so half of 4 times 5 is your fourth triangular number.
So we essentially turned it into a rectangle so that we could make it a multiplication question. In turning it into a rectangle, we effectively doubled it. So then we needed to cut it back by half. We needed to divide it by
because that's generally how we solve the area of triangles, right? Like, because if we think about this triangle inside of a square, generally, like, when you want to figure out the area of a triangle, you imagine it inside of a square and then you like divide by 2. So that's what we're doing here. Okay. It's just that because they're like, it's not continuous, it's just individual dots. It didn't quite line up quite right. So instead of being half of the square number, it's half of like a little bit more than the square number. It goes off to the side here. Okay. In a perfect world, triangular numbers would be half of the square number, but it's not. Nothing could make it so. That's how I feel. So anyway, the point is that you can if you have trouble coming up with this, you can look up your sequence and see if there's a formula there for it, which there is. I was actually looking through this, and I did see if I can find it again.
So my next question would be, is there, and while you're looking at this, but there's no way to do any additional intersections. It's not possible to add any more. And I think that's what we just showed, essentially. You can only intersect with every existing line. You can't intersect because they're straight lines. So you can't intersect with any of the lines more than once because they're straight. And so, therefore, you can't intersect with any of the existing lines more than the number of existing lines.
No, that's a really good question. Yes. That's exactly what the sort of question you should ask in a math class. You should say, like, wait, did we prove this all the way? Right? Like, could there be another way for a line to, like, intersect with a previous line more than once? And straight lines on a plane, you can't, but maybe that's not obvious, and maybe you'd want to go back and try to explain why that's not obvious. Straight lines, for instance, on, like, a curved surface sometimes can, or whatever. Right. So actually looking at the entry on the encyclopedia. I found this line here. It says maximum number of lines formed by the intersection of n plus 1 planes, which is like the equivalent of what we're doing, only kind of like up a dimension, right? Like instead of intersections of lines, it's talking about intersections of like planes, which is planes are just, flat surfaces, right? They're just like 2D sheets.
Okay.
So it's the same thing. I think it's like ironic that they have that, but like not intersections of lines, which I feel like is more simple. But I think mathematically they're probably the
2D
same.
2D plane is 2D, and we're dealing with
Yeah, it's just bumping it up a
one-dimensional
dimension.
lines. Uh-huh.
And so the number of points formed by intersections of lines, it's the number of lines
really
formed
cool.
by intersections of planes. It'd be interesting to like think about whether you could bump this up another dimension, except that thinking in 4 dimensions is like the hardest thing ever. Anyway, I have a lot more I could talk about this. There were a few other things on here that I thought were really interesting. I really like this one. The number of distinct handshakes in a room with n plus 1 people. I kind of like that because I feel like I
don't even know what that means.
It's like, so it's saying if you have a room,
in the same sense,
if you have like a room with 3 people, like we do here, there's 3 possible ways we could all shake hands. Like I could shake hands with Zach, you could shake hands with Zach, or I could shake hands with you, right? Which I kind of like. It's sort of like a concrete version of what we were doing with the lines, right? If you think of every line as a person and every intersection as a distinct handshake, then that would be the same. And in a way, that sort of got me thinking that like really what this is triangular numbers map out like the way things can interact with each other. Like so if you have like a certain number of objects, say I'm just going to draw objects as dots, the triangular number will tell you what are the maximum number of connections essentially you could have. Wow, I'm really not drawing straight right now.
Yeah, you need that ruler back.
Right? So this is called a complete graph essentially. But it's a graph where like you have points and they're all connecting in the maximum number of ways. And so really like that's what we're talking about with triangular numbers, which I never like thought about before. Yeah, exactly. Whenever you have like if you have like objects. If you have like 10 teams in your conference and you want every single team to play against every other team, the like number of games that will be the 10th triangular number, actually the 9th triangular number because it's n plus 1. Like I said, it's offset by 1.
Okay, so wait, apply the formula there so I can see it, if you don't mind.
For this graph or for 10 teams?
Yes, for this graph.
Oh, so for this graph there.
Oh, you were just pulling 10 teams out of.
So for instance, if you had like 10 teams, then you just plug it into this. Like I said, it's n plus 1. So like you see here, like it's like offset by 1. Remember? No, actually the other way around. So like 10 is like the 4th. So anyway, if you had 10 teams, you would want the 9th triangular number, and you would just plug in the formula 9 times 10 divided by 2. So that is 45, I think.
Okay, finally
double check
clicking.
that I did this right.
So there's 45.
Yeah, 45. So if you have 10 teams,
and you want every team to play with each other, you'd have to play 45 games.
Yeah.
Games.
No, exactly.
They
go
cool.
fast. Not as fast as square numbers, but
no,
half as fast.
But in practical terms, that's pretty fast.
Yeah. Actually, when I was working this out, after I was like thinking about this, the number of edges in a complete graph of order n plus 1, that's essentially that's kind of a technical way of phrasing what I'm talking about. Like if you have edges are the lines connecting different dots on a graph. So it's the number of edges in a complete graph, the number of edges in a graph where all the lines are connecting all the points, right? So anyway, this was I can go down other rabbit holes, but I actually thought it was really interesting. I probably read somewhere that triangular numbers count the number of relations between objects. That's the sort of thing somebody might have told me once, but it didn't sink in until I was sort of doing it myself. I was like, oh, that's what I'm counting here. The number of ways that, the maximum number of ways that objects can can interact or relate to each other. So anyway, I thought that was kind of cool. Like I said, this started out as like a really simple problem that you can probably solve in one sitting, but the more I thought about it, the more interesting it was. And like I said, there are other things you can do with it. Like I was thinking about if they are parallel. If you have parallel lines, there are ways of like calculating that. It's a little more complicated, but it kind of made a cool pattern. So that's something that
we might do further along
work out
down the road
in their own time, or we could do later. So anyway, that is my math club presentation. So that's the sort of thing you can do. Just present something you're working on and anything you've learned about or thought about a math problem. And it could be a problem that's already well known or whatever, and just something you studied or whatever. I think we're gonna use that maybe as an example down the road. Maybe we'll look at some established problems and we can just kind of present them to each other. But there's lots of things you could do. I just think it's really fun to do it in a group. This was really fun explaining this because I just had this in my head, and now we all have it in our heads. So
that's cool.
Well, thanks for sharing.
It's what a joy. Anyway, that's what I have for Math Club today.
Thank you for listening to the Making Mathematicians podcast. We hope our discussion has helped or inspired you in your effort to learn and teach real math. If you have a question you'd like to ask us, please leave a comment or email podcast@makingmathematicians.org. If you'd like to learn more, check out the complete Making Mathematicians course at makingmathematicians.org.